Hello, everybody. My name is Gene Kogan, and this is my second time recording a conference with the best. Thanks to the organizers for having me back. This is still kind of strange for me to be just looking at my computer screen and trusting that there are people out there, but it seems like, well, it worked last time, so hopefully there's a few of you who are interested in the kind of work that I do. I'm just going to go straight into my slides and get into what I do. Just going to go ahead and share the screen. You're looking at a texture synthesis. This is something that I'm going to show you a little bit later. It's kind of just a little technique that I've been working with lately. If you're interested in any of the things that I'm going to show you in the next 45 minutes or so, you can find my work at genekogan.com and ml4a.github.io. which is a website that I've been maintaining that I'm going to talk about a little bit later. And you can also find me on Twitter, Gene Kogan, and ml4a_. So let me first tell you a little bit about what I do, or first I'll tell you about my background and a little bit more about what I do more recently. So I have a background in applied mathematics and machine learning. I was kind of working with machine learning as an undergrad when I went to college. And I really became interested originally in the field called music information retrieval. So the top two graphics are from a previous career that I had for a couple of years, working on applying machine learning to the field of to music, basically retrieving relevant and interesting information for let's say playlisting technologies or creating music composition with technology. I was making graphics like these, trying to find, for example, the relationships between different tag words that are used to describe music on various platforms online. And so this is kind of more engineering oriented, but because the subject was music, there was a lot of people who are working with music from a more artistic or designer level are very much interested in this kind of technology. So I was constantly exposed to people who are interested in things like music composition, music performance, and technology for more performance use cases of music. And so this kind of got me thinking about how machine learning can be used for for creativity. And one of the early projects that I worked with that kind of really kickstarted this was working with a good friend of mine named Jeff Snyder, who is a builder of exotic musical instruments like the ones you're looking at down here. This is called a burl, which is an electronic wind instrument that he designed in order to be able to basically use machine learning to train a relationship between the input sensors that it was detecting from a human performer and the parameters of an output synthesis. So like some digital musical instrument that is being controlled by this, what's effectively a controller. It doesn't make sound by itself, but it has all these sensors on board, these capacitive touch sensors for your fingers, and a very smart mouthpiece that had a breath pressure and embouchure sensor. And so we created an interface that would let people, let musicians train a relationship between the desired input parameters, that come about from playing the instrument and, the sound that it was making in some digital instrument. And so this, was kind of bridging these two sides, very scientific and very artistic sides of machine learning together. And that became, I became very obsessed with it down the road. I learned very early on that I was not a very good research scientist because whenever I would learn about new sorts of machine learning algorithms, I would immediately apply them to something kind of useless. So, for example, this was an early project called Color of Words that I did sometime in 2011 using self-organizing maps, which are, of course, like these days, not very popular algorithms anymore in the age of t-SNE, I suppose. But self-organizing maps were kind of interesting because they were some of the first unsupervised learning algorithms that were easy to implement on computers. And so what I could do was, I became very interested in the sort of hive mind, right? Like, I started asking questions like what colors are associated with words? and how can we discover them. And so the technique for this would be, for each of these words, I would do a Google image search and then download the first several hundred images automatically using some scraper, which was much easier back then, incidentally. And then I would use a self-organizing map to visualize the pixel distribution, so the colors of the pixels. And so predictably, you would see that winter, spring, summer, and fall kind of evoke the colors that are associated with those seasons. Winter is very bluish and white, and fall is very sort of, orange and green. And so it kind of makes sense. Of course, these are different biomes. Rainforest is a deep green. Desert is sort of mostly brownish. Different holidays, like Valentine's Day, is all pink, of course. Fruits, broccoli is green, apples are red. And this was the sort of stuff that I was really interested in the first couple of years that I was doing machine learning. And I didn't really, I became kind of disenchanted with machine learning scientific research because, I felt like, okay, well, we're making incremental progress, getting accuracy improvements of 1% per year, something like that. But what can we do with it? What would be interesting to all of the people in my life who didn't really, necessarily have any interest in this field from a technical standpoint? How could I bring meaning to them? What would they find interesting about it? And so this was kind of the direction that I began to take increasingly after I began to sort of wind down my work in music information retrieval and become more of what we call a new media artist today. So now recently, the last few years, I've been working a lot with deep learning. Of course, just like everybody, deep learning has really captured the public's imagination, and it was really kind of, I think, probably one of the most interesting aspects of the deep learning craze of the last few years has been the extent to which it's crossed over into mainstream media and mainstream society. And so this is kind of why I think that we're in something of a new golden age for machine learning and AI, because, in the 60s, when we were first kind of began to dream about AI, it was something that the public was quite involved in. The public was very much interested in all of this new AI technology, and that kind of died down over in the 70s and 80s. And I think it's beginning to pick up again recently. And for one, and the biggest reason is because I think a lot of the new machine learning technologies are well, two reasons, I'd say. One is that it's becoming more and more relevant to other fields, so disciplines that are outside of scientific research. And the second reason is because it's beginning to kind of have cultural ramifications. So when we can do things like the following, so this is using something called attention GAN to produce an image from a sentence. So, you type in a sentence like "a woman is eating a delicious sandwich," and the neural network hallucinates, as we say sometimes, an image that describes that sentence really well. And so this is kind of really interesting to us because it's along the same lines of what I was interested in color of words, trying to use machine learning to understand humans. What do we think about? How do we associate words with images? And so it's become a lot more meaningful than I think it was in the years preceding that. And I like this piece because it kind of ties in three different parts of the ecosystem that eventually made. This was in lots of articles, like popular science press. And it was essentially, there's a kind of three layers to it. The first is attention GAN, which is at the base layer. This is some work that basically does text to image synthesis, and it's actually available online in GitHub and open source. And then a good friend of mine named Chris Valenzuela, who is a resident at ITP NYU, where I'm teaching. I'm going to be discussing that later. He created a tool called Runway, which allows artists to very easily use something like attention GAN and lots of other deep learning libraries. And then another AI artist named Janelle Shane used Chris's package to make a whole bunch of really interesting images, and this kind of caught the attention of a lot of popular press, and we started seeing images like this in different sort of publications. And so I really like that the fact that there's kind of multiple people involved in bringing this to public attention, what would otherwise be a very esoteric subject that's kind of only known to machine learning scientists. Now, the reason why deep learning has been so successful at capturing the attention of media artists like myself is that it now works at the media level. And I'll explain what I mean by that. Originally, if you were a computer vision researcher, you were kind of working a lot with a lot of very time-consuming and engineering intensive feature extractors that would have to be hand-coded. So things like HAR cascades and histogram of oriented gradients, hog features, SIF, SURF, lots of these different acronyms that are take a lot of domain knowledge to really understand how to use. And so it was very time consuming. There was a lot of code in different sort of non-homogeneous environments that had to be brought together. And it was very task specific. So if you were a computer vision researcher, you had to know a whole lot of things about computer vision in order to do machine learning on it. But if you, nowadays, what's happened, and I should say that if you were a sound researcher, you would have to relearn everything to do the same thing with sound, right? So, but now what's happened is that deep learning has kind of swallowed the entire process of feature extraction. Everything is now trained end to end. The code and the algorithms are extremely homogeneous, which is to say that it's many layers and many neurons, effectively the same thing, just 100 million times the scale that it used to be. And and that's very useful for us because it generalizes very nicely to different tasks. You don't necessarily have to have a lot of domain knowledge in both audio and video, let's say, if you wanted to do interesting work in both of those fields. And I think that's really crucial for media artists because we're not necessarily domain experts in computer vision or in sound. We're really interested in the interplay between these things, trying to create interesting interactions, right? And this is the kind of thing that really helps us because therefore we don't necessarily we can use one tool, let's say, or one approach to integrating all the senses into the experience, visual, sound. Increasingly I see things that are oriented towards smell and touch. So I think all of the senses are kind of being brought into the fold. So what I'm going to do now is I'm going to show you some work that I've done recently myself, kind of building on many years of interesting research. I do work a lot with these visualization approaches, pixel optimization approaches that you might associate mostly with DeepDream. But they go back a little bit farther than just DeepDream. So starting around the late 2000s, maybe 2009, 2010, and continuing onward, we've been really interested for a long time in using machine learning to or understanding the properties of neural networks. And so one way of trying to do that is to try to activate different neurons that are responsible for detecting certain kinds of features. And you can use optimization-based approaches to try to excite neurons that are recognizing different kinds of objects. So, for example, if you're interested in visualizing what a neuron sees when it thinks of a bell pepper, you can kind of do that, right? So, and this is some work by Simonian et al., I think from 2009. And in 2012, Kwok Lei and his team at Google downloaded lots and lots of YouTube videos and produced the optimal stimulus for a cat neuron, right? And this really kind of captured the public's imagination. It was really a precursor of the deep learning craze that we now see today. And this kind of was taken to the next level in 2015 with some work by Google researchers Alex Mordvintsev, Chris Olah, and Mike Taika, who basically, you can see some of this in their blog posts. They were using this feature optimization techniques to, but actually creating images that were beginning to capture, my imagination and the imagination of lots of people because they were increasingly evoking sort of real everyday objects. And this culminated with DeepDream. So of course, DeepDream was was in my mind, I think, the moment that the field of machine learning really crossed over into media arts and generative arts and so on. Because at the time I was a new media artist and I was doing a lot of things like interactive installations and making sort of generative art pieces, but it felt very different from my practice doing applied machine learning. At the time I was doing still music information retrieval. And so something like DeepDream was really the first time where I sensed interest from the art world, let's call it, in machine learning and AI. And so I began to really try to work, at bridging these things together, kind of trying to work with both machine learning and the things that I become interested in new media at the same time. And there became an ecosystem, I think, starting in 2015 and kind of just increasing year by year until now. And DeepDream was kind of a nice hack of this this optimization technique, in which the optimization was not used to enhance a particular neuron of interest, but it was used to enhance whatever the neural network was already seeing at the time. So it was all about enhancing the patterns that it saw. And so this was really a curiosity, and I would trace a lot of the artistic work that kind of went into this technique in 2015 to, in particular, Alex Mordvintsev, who came up with DeepDream per se, and made these amazing graphics like these, as well as the work of Mike Tyka, who really kind of was a big inspiration for me in working with this technique, because he came up with a lot of really interesting extended techniques for working with DeepDream. So things like starting with noise, just starting with white noise instead of like a real image, as well as exploring masks and sort of different ways of distorting the canvas and making videos. Mike was really, I think, the first person to really work with the explicit purpose of making art, the sort of stated purpose of making art. And I began to explore this technique as well. And I've been interested in a long time. And actually, I'm going to show you some resources for doing this kind of stuff as well later on at the end of my talk. I became really interested in applying masks. So the whole thing with DeepDream is that it's an iterative technique. It uses optimization, and so it's iterative. And so at each iteration, a tiny gradient is added to all of the pixels. And so I became interested in, and this was something that Mike did as well. I became interested in masking these gradients, so multiplying them by some, by a matrix between 0 and 1 to kind of let's say quell the gradient in different parts of the image and enhance it in other parts, and then combining different neurons so that you could do things like sort of like melt, one neuron activation into another neuron activation. So here in the middle, you can kind of see the intersection between these two different these two different neurons. And so I began to make graphics like this. I was using the original TensorFlow code for working with DeepDream and adding all of this mask optimization to it. And so you can kind of see what's going on here. There's two neurons that are being activated, and on the left side you have most of this feature, and then on the right side you have these, these kind of egg-looking features. And in the middle, it's kind of a little bit of both, so there's sort of this crossfading of the masks. And so what ends up happening is that the optimization tries to create pixels that have properties of both of these neurons, right? And so here, this is also like exploring different kinds of masks. The mask here is circular, so kind of concentric circles. And you can also make video with this technique, and this is something that I became also quite interested in. And the video technique uses feedback, because you always have an input image to the process, and this was kind of quite a curiosity for me. I also figured out a way to make them loop perfectly. So if you're looking at these two videos, this is basically concentric circle masks. And what's really interesting about these is that they're perfect loops. So each video is actually only 3 seconds long. So if you watch it, you may not notice that it actually keeps on going left and right, back and forth. And I can show you right here. You see that the play bar at the bottom is going through a 3-second loop. And the technique for this, I've been meaning to make a software repository that shows how to do this. It's actually relatively straightforward, even a little bit brute force oriented. But basically the idea is to kind of use this feedback process, but actually gradually, well, this may not make sense actually to just say it. I have to put the software online, but basically it just kind of keeps on going in a perfect loop by gradually interpolating from using the previous frame as the input to using the next frame as the input. So style transfer is a closely related technique, or at least the original style transfer, which used optimization. And style transfer is all about recomposing one image in the style of another image. So this is, of course, the Mona Lisa, and the Mona Lisa regenerated as though she were a Picasso painting, a Van Gogh painting, and a Monet painting. And style transfer is a really interesting technique. I've also been interested in using it for a long time. I've been making videos with it using the optimization technique. So this is this disco ball made by a generative artist named Mr. Div, and it's being restyled by Gustav Klimt's The Kiss, right? And this has been of interest to me. And a few, let's say maybe half a year or so after the original optimization-based style transfer became popular, a technique was emerged to use neural networks to essentially do it in a single forward pass, which made it fast. And so I became really interested in the fast version of this because as an interactive media artist, I'm interested in interactivity. I'm interested in things that work in real time. And so I started creating an installation that I call Cubist Mirror. And Cubist Mirror is basically just a style transfer mirror that has a webcam pointed at you and then regenerates the image in a particular style. So I'll show you a video. This was the style transfer mirrors, or Cubist Mirror was displayed at the Toronto International Film Festival, which I took part in about a year ago. That's a friend of mine named Lassie who's interacting with it. You could see that that's a Hokusai style. And here this mirror is in Kandinsky. And, kids love it. I think that's probably the takeaway that I would most quickly say, is that kids really, really love it. And, it's playful, and it's kind of a new thing that people, are beginning to slowly become more and more familiar with. I think we'll see these things in smartphones and in TVs and so on, like very, very soon. Now, very closely related to the optimization-based style transfer is texture synthesis. And texture synthesis really is style transfer, except it has no content. So this is basically a contentless style transfer using Google Maps as a source texture. And it's many people have pointed out correctly that it's overfit to San Francisco, and it's quite true. However, this is not a real place, as you can tell by the sort of very strange looking labels on the map. Now, texture synthesis, like DeepDream, can be you can make videos with it, and so I began to make these loops. As I mentioned before, this is like the DeepDream loops that I showed you. This is actually just a 6-second long perfect loop that is doing this sort of infinite zoom texture synthesis using this looping technique that I mentioned in a few slides ago. Actually quite similar. There's a few minor differences, but it basically uses the same approach. And so I've been really, really kind of like fascinated by this, because generative artists are often very much try to constrain themselves to create perfect loops. And it's quite difficult, but somehow you can do it, but usually using a lot of engineering. So to try to figure out a way of let's say making perfect loops using trigonometry, right? So that 0 degrees and 360 degrees are the same, and so maybe if you have some parameter that shifts gradually from 0 to 360, and then you loop it, you'll get perfect continuity. But with the texture synthesis, it's hard to even see what the different components of this are, right? So this is kind of for me been really, really fun. This is the same thing, except it's a texture synthesis of Hokusai. So this is the Great Wave off Kanagawa, which is a really, really fascinating technique. It's a very, very it's a beautiful painting from the 1800s. Actually, a wood block, and again, perfect loop, evoking the texture of these waves crashing down. This is Kandinsky. So this is Composition 8, the famous, one of the first abstract paintings, as it's said. And you can use the texture synthesis technique to also make sort of collages. So this is texture synthesis that uses as its input many, or maybe something like a dozen or 2 dozen paintings by Jackson Pollock. And so, of course, he has a very distinct style. the sort of drip painting technique, and this is kind of just like sampling from it and making these really cool abstract images that evoke the style of that particular painter, right? So this is the same thing except using Frida Kahlo. Frida Kahlo made a lot of self-portraits, and so you can kind of see random eyes and eyebrows. She has very, very strong eyebrows, of course, everyone knows. And so these are, you can kind of see those features coming through. I think that's a nose right there. And then there's Salvador Dali. I think there's some melting clocks, as you can kind of tell, sort of Salvador Dali classic style. Moving along, generative models. Now, generative models are just completely fascinating to me. And being a generative artist, I'm interested in generativity, right? And generative models are essentially neural networks that take as their input many, many tens of thousands or hundreds of thousands or even millions of images, and then they're able to synthesize new images which look as though they came from the original data. And they usually take as their input some sort of what we call a latent input vector, right? Some sort of which is usually sort of homogeneously structured or like sampled from a unit Gaussian or something like that, like a homogeneous probability distribution, and or I should say a uniform probability distribution, not a homogeneous. And they're quite interesting because you can play with the features of them using this latent input vector. And there's kind of two approaches that are quite popular to this. So autoencoders are one. These are neural networks that learn these are neural networks that learn a generative model by essentially by trying to compress the information in the original data set into a low dimensional compact latent space, right? Which is some sort of a bottleneck in the network. Otherwise, it's trying to just reconstruct the images. And autoencoders have been around for a long time. There's a lot of controversy as to whether or not they're useful, but they do make pretty good generative models, and they were some of the first neural network generative models that worked well. Now things were kind of and this is of course another view of autoencoders. You can think of them as almost like a compression that compresses the data into high-level feature vectors, high-level features, and then it uses a decoder to take the high-level features and produce, images of, let's say, faces or whatever your data set consists of. And the neat thing about this is that once you have this model, you can just throw in whatever numbers you want. You can throw in random numbers into the decoder, and it will produce, plausible-looking faces, if you happen to have trained in faces. And this has lots of applications, things like denoising data. There's borrowed this slide from my class. So we're not actually going to get to this later, but variational autoencoders in particular are the ones that have interested artists. Generative adversarial networks are also quite interesting. So these are these have really kind of taken generative models to the next level. So these are quite similar to autoencoders, except they kind of decouple the generator and the discriminator, as it's called, and then they're trained kind of together in an adversarial process. And lots of people, of course, Ian Goodfellow spoke at with the best previously, and so he probably did a much better job explaining what generative adversarial networks are than I am right here. But of course, for artistic purposes, it's quite clear what the appeal is. They make really, really amazing looking samples. And I've been really, really interested in this for the last couple of years. I think the first paper that demonstrated generative adversarial networks for the purposes of making images was these deep convolutional generative adversarial networks by Alec Radford, Luke Metz, and Samit Chintula in late 2015, in which they applied this the GAN framework with deconvolutional layers, and then demonstrated that you can make images of faces and bedrooms and other things that they had in their original paper that were not only had a higher quality than autoencoders, but were beginning to really look like the real thing, right? They were crisp, they were realistic, they had very high level of detail, and most interestingly, they had this really neat latent space that you could play with. So for example, if you found the latent vector that would produce a man with glasses and subtracted the latent vector that produces a man and added woman, the vector for woman, you would get man with glasses minus man plus woman equals woman with glasses, right? So this is kind of a really, really fascinating property of these, that you could kind of perform arithmetic on the generative space. So for my part, just shortly after they released that paper, I found a data set of handwritten Chinese characters collected by a university in Beijing. It called HITOR3C. You can look it up. It's a data set of handwritten Chinese characters that are, basically used for optical character recognition research. And I thought it would be fun to put them into a DC GAN and have a neural network create synthetic characters. So these are pairs of characters, and the ones on the left are real, and the ones on the right are fake. They're created by the network. And you can see that they're quite convincing, especially for simple characters. And this was all part of a project I called A Book from the Sky. This is an artwork that was, it's named after an artwork by a Chinese artist named Xu Bing, who's quite well known for fabricating thousands of wood blocks depicting fake Chinese characters. And this is kind of the opposite. These are he made, let's say real versions of fake characters, and I make fake versions of real characters. But what's really neat is once you have a generative model of them, you can do these interpolations through a latent space. You can kind of tweak the numbers in the latent vector and produce these gradual shifts in the high-level characteristics of the output. And so you can kind of explore the different characteristics of handwriting. And these are just different examples that I found appealing. And of course, DC GANs can be conditioned on labels. And so if you have distinct characters, you can actually try to do interpolations between them. So you see that these are interpolations among a related set of characters, people and culture, for example. And this for me is really interesting because it kind of gets to the heart of language. It makes me think of, characters that never existed, characters that might pertain to concepts in between characters that we do have. So like, what is the character between people and culture, and what does it mean? And you can think of almost like our conception of language as a latent space of sorts, a latent space of concepts, and we only have characters for certain points in it. And so this is kind of like, for me, been a huge appeal. Now that was 3 years ago almost, and more recently we've had incredible progress in GANs, and it's been just amazing for me to watch. Originally, when working on A Book from the Sky, the best we could do was produce GANs at a pixel at something like 32 or 64 pixels. And now with some recent work from NVIDIA, we can make images that with GANs that are as much as HD, basically 1024 pixels in this case, or maybe even 2048, and going up higher. And they capture such incredible detail, so like you can see the hair follicles, you can see stubble on people's beards, and we're really getting to the point where we can essentially make, realistic and convincing looking faces that very much fool a casual human observer into thinking they're real. And so we really have to start to think about what that means, what's going to do to our technology, to our society, when we can convincingly fake people's faces. Progressive GANs, the software is online, and so and including a lot of the models. So I downloaded some of the models and tried to kind of explain to people why I'm so interested in these, why I find them so fascinating. And so this is the latent space of cats and screens and cars and bedrooms and bicycles and lots of others. You can actually download these models online. And there's some simple code from NVIDIA for actually just like tweaking these latent spaces and actually creating interesting looking videos like of this sort. These are contributed by other people who trained their own progressive GANs. The one on the right is on eyes that were collected by a frequent collaborator of mine named Andreas Refsgaard. The one on the left is by a fellow named Wei Zhok, I think. This was just posted to Reddit maybe a few months ago, and it's generative ramen, and it's beautiful, right? I think, in my opinion, it's quite beautiful. An artist named Robbie Barrett kind of trained progressive GANs on nude portraits, so that's kind of really quite interesting as well. This made a lot of news because the internet loves naked people. So Another category of generative models that are quite interesting is image-to-image networks, so PixDepiction. These are generative models that take a label map, for example, and turn it into a photograph. So label maps to building facades, that you might imagine could be useful for, like, let's say, a designer or an architect to be able to mock up building textures for the labels that they create, doing things like turning black and white photos into photographs, turning sketches of things into photographs, changing the day-night characteristics, changing the seasons of things, converting satellite images into maps and things of that sort. And PixDepiction has really captured the interest of artists over the last couple of years, over the last 2 years, let's say, because it really is kind of a generic image filter, and so you can create a lot of really interesting interactions trained on just maybe only 1,000 images that you need, something like that. And so that has been quite fascinating as well. This is recently some research from Karasan et al. Basically something like PixDepiction, except interactive. So it lets you mess with the different characteristics of scenes, like outdoor scenes, change how cloudy it is, change how the seasons and things like that sort. And this is kind of, for me, I think this is really interesting because I think design software is going to look very much like this in the future. So things like Photoshop and Illustrator, they're going to increasingly have features that are driven by neural networks and machine learning to create sort of advanced image filters and so on. I used this for a project called Invisible Cities, which was a work that I did basically downloading maps and satellite images and then converting the maps into satellite images. So you could do something like a city style transfer. So here, this is Milan in the style of Los Angeles, and then Milan in the style of Venice. And what you do is you train PixDepiction to convert the maps to satellite images, and then you do that for multiple cities, and then you can use the map of one city as the input to the generative model for another city. And that's kind of where these come from. Similarly, you don't have to use the original maps. You can actually just draw them, right? So this is like a drawing of the place that I did. This is a collaborative project at a workshop that I did at Open.lab in Milan, Italy. And so you could just draw one of these and then make, drawing like your own sort of fantasy landscapes. And this is kind of like something, this was my first PixDepiction project. One artist who is a good friend of mine and does a lot of work with PixDepiction and does a lot of really amazing work with PixDepiction is Mario Klingemann. And he kind of first came up with the idea of using face tracker as an input. So like face tracker as an input label map to PixDepiction. And he makes all sorts of really bizarre generative art of this sort. And he makes interactive things as well. This is something called Uncanny Mirror, which he and that's me in the Uncanny Mirror. I was just with Mario at the Seoul Biennale, and he had this on display. It's really awesome work. And I've riffed on this idea to create my own little face-to-face experience by converting myself into the president of the United States here, Donald Trump. So first you train the face markers to the original faces, and then you can do a sort of face swap. And of course, this is from 2 years ago, so it looks pretty bad. No one's going to think that's the real thing. But now we're doing increasingly realistic versions of this. And so people really have to begin to confront this fact. What's going to happen when we can essentially just, hallucinate arbitrary people's faces? We can, any person on the street can fake the president's face. So what does that mean for the future of the internet? What does that mean for the future of social media? More recent work from NVIDIA. This is just from a few weeks ago, vid to vid. And I'm just showing it because it's the most realistic version of image synthesis that I've seen so far. Just, making incredibly realistic and detailed scenes just from data. Really incredible stuff. And so you can kind of see the realism. These are, of course, a much better version than what I had 2 years ago. This is now, quite convincing. You can see that they're even blinking really well. And so doing sort of, these are all synthetic faces, right? So edge-to-face synthesis using NVIDIA's work. And it's really amazing stuff. Same thing, except doing pose to body. And actually, I have a better version of this. This is just from a few. This is from just a few weeks ago. Something called Everybody Dance Now. So they are. So you can kind of see what's going on here. This is the researcher Caroline Chan, and she's having herself synthesized using this source video. Right. So this is an actual dancer. They're detecting his pose and then generating a really, really convincing synthesis of the researcher here. We can kind of fast forward. So a little bit more. I love that this is a research video, because, research videos with pop music as soundtracks and doing stuff with dance. And this is the kind of stuff that really captures the public's imagination. I really want to see the researchers kind of prioritize this kind of work more, because it pulls more and more people. It really inspires people to work with this kind of technology. Yeah, and then this is Bruno Mars, I think. Right? The ballet, of course, this is the really most difficult one because it's quite hard to track the ballet, right? So, of course, the researchers don't really know how to do ballet, but, and I'm telling you that this in, 1 year, maybe 2 years, this kind of stuff will be in the smartphone app. So you'll be able to make yourself dance convincingly just from a little bit of source video. So just imagine in a couple of years, this kind of stuff. And I just want to briefly mention Cyclogen in the research because it's Pix, except it doesn't require the samples to be paired. And so this was a video that went viral about a year ago of Cyclogen converting a horse into a zebra. And of course, the technology is not perfect. It makes lots of really funny mistakes sometimes, but it kind of, well, if it does even half of this good of a job, it's already quite interesting. So getting close to the end here, I just want to mention, my motivation for this is really kind of to have fun, because a lot of the ways that a lot of this technology can be used is in a playful way, in a way that's uplifting, in a way that kind of makes use of people's creativity. And that's, I think, the most engaging way to really learn about this stuff, because, people want to, when people are learning about a technology, my hypothesis is that the best way to do that is in a way that allows them to express their creativity instead of, working to solve some sort of a particular task. And so having fun is kind of like my motivation for this. So of course, this is dense captioning of a certain famous person here. And having fun is kind of doing things like creating interactive demos that identify croissants and coffee cups and attaching them to music, doing dense cap on top of DeepDream, mostly a lot of making jokes online, you might say. And I make a lot of these demos that you can download online. If you look up ML4A, you'll see things like, interactive convolutional neural network viewer, working with a technique called TSNE to organize audio and image samples and things of that sort. These demos are all available on a resource that I mentioned briefly earlier called ml4a.github.io, which is a website that I've been compiling for the last 3 years that contains resources for getting started with machine learning for artists, for designers, for people interested in interactivity, for really basically everyone who's not a computer scientist or engineer. And so if you're interested in the kind of stuff that I do, if you want to make your own tools and your own art, I highly encourage you to visit this resource, and please do tell me if you like it. We also have a Slack channel. So there's quite a community that's formed around these tools. And lastly, a lot of this has created, I've been giving workshops for the last couple of years, lots of machine learning for artists workshops. You can if you go to my website, you'll see I have a log of them that has information about them. And lots of happy people, using machine learning in creative and interactive ways. And I'm available for workshops. So if you're interested in having a workshop in your location, please do get in touch with me. I love giving these. These are for me kind of like the best way to really get this stuff out there is to interface with people directly in a room. and show them how to use these tools in the way that they find most interesting for their own crafts. I'm also a teacher, so I besides for the workshops, I give classes. These are video lectures that I recorded a couple of years ago at ITP, the first time I did a class at NYU. And you can see those classes online. Those are, again, under mlfreid.github.io/classes. And along those lines, I've actually just begun teaching a class this semester at NYU called The Neural Aesthetic. And if you visit this link, you'll see that that the syllabus is online, as well as slides and video lectures. These are going to be around 36 hours of class that's going to be put online entirely, all the video lectures and things and so on. So this is kind of my next big task. If you're interested in this, I very much encourage you to download the videos and watch them and tell me what you think about them and kind of link up. So that's all I have for you today. Again, you can find my work at genekogan.com, and I'm on Twitter at genekogan. And you can also find a lot of the stuff at MLFreid, a lot of the resources at mlfreid.github.io, and also MLFreid on Twitter. Please do get in touch with me, join our Slack channel, have some workshops, download the tools. They're all free and open source. And yeah, tell me what you think about them. So that's all I have for you. Thank you very much. And I guess we have about 15 minutes left. So I think there's some sort of a Q&A session. So if anyone has any questions for me, I'm going to stick around for just a little bit. Regarding generative models, how do we know that it is not just producing an image it has already seen with some minor changes? Are there ways to verify this automatically? It is actually quite difficult to do this. So there's no way to do this directly, at least with GANs, because they don't actually have proper inference capabilities. There are ways of doing it, like there's various sort of hacks around this, and I'm actually not the best person to ask about it. You should ask Ian Goodfellow, I think, because you can try to use other neural networks. Let's say they're trained to identify images or maybe analyze the features and then try to find nearest neighbors. So that's the typical thing that you see in papers, like nearest neighbor search. So trying to find the nearest neighbor with the same activations, and then basically just kind of using a qualitative approach to analyze. There's really no way to measure it rigorously, which is a shame. And GANs are sort of criticized sometimes for having a low level of diversity. So a lot of the samples do tend to look the same, but they're getting better, I think. So they do produce a lot of novelty. Oh, another way you can tell is that, if the latent space is quite smooth, then that's a good indicator that you have a generative model that has learned to generalize. If it's producing almost the same thing in every part of the latent space, then that's probably a good indication that maybe you have some overfitting. Yeah, good question. No problem. Can you please tell your opinion on TensorFlow.js? What kind of opportunities it will bring to ML space you think will be a game changer? I'm glad you asked. I love TensorFlow.js. TensorFlow.js, for anyone who's not aware of it, is basically a WebGL implemented browser web-ready version of TensorFlow written in JavaScript. That has been developed by some people at Google who I know online, basically doing a great job. And it makes it possible to bring a lot of the stuff into the browser. And, a couple of years ago, if you had told me that you could run deep neural networks in the browser, I would have not believed you, right? Because it's just kind of hard to believe that any of this, because browsers are quite limited in the number of resources they get to control. And of course, security limitations and things like that. So TensorFlow.js really bridges the gap between these things. And I'm also, I should mention, I'm quite excited about ML5. So ML5 is if you look up, actually, let me quickly share my screen. I'll show this. ML5 is a venture that is being organized by some of my good friends at ITP at NYU. And ML5 is actually as you can see, it's something of a wrapper for TensorFlow.js that's targeted towards artists and designers and people who and creative technologists. So ML5 is really is also a game changer because it makes it super easy to use deep learning techniques in the browser. I mean, of course, like TensorFlow.js does that as well. But TensorFlow.js is you might say is targeted towards a somewhat lower level of the stack, and so ML5 is kind of like bringing in people who have almost zero experience with machine learning and getting them to begin to understand these things more effectively. So yeah, I really like TensorFlow.js and ML5. I'm quite optimistic that they're gonna be, as you say, a game changer. Good questions. Regarding the class that you're teaching at NYU, is there any way regarding class that you're not teaching at NYU, is there any way students not currently enrolled at NYU attend it in person? So, well, okay, so the short answer is no, because NYU is a university that does limit its admission. So there's actually just like, I do have auditors, but the room is quite small. So even with the auditors from NYU, there's not many more people that can fit in it. The way that's kind of like, I wish I could have anyone join, but of course these are universities. Now the way that I try to mitigate that is I try to take literally everything that we make in the class is put online. So I'm going to share my screen again and actually just show you. So I showed this link just a bit earlier. If you go to ml4a.github classes/ITP F8-F18, that's a capital F, you'll see that the slides and the videos are all put online. So the slides are just hosted. They're my keynotes. I'm actually going to do this with this keynote as well. And then the videos of the entire screen recordings are put online. So I record the entire class, my screen and my lecture, and then I annotate the videos and I put them online so that anybody can watch them from online. It's not as good as being in person. I wouldn't pretend otherwise, but it does I think hopefully bridge the gap a little bit so people can actually watch these in their own time and try to interact. And then the other thing that I try to do to bridge the divide is we have a Slack channel on ML4A and try to create a community around these tools. Of course, everything that I make is, including all the tools for the class, is open source without exception. Everything is done open source. Everything is free to use. And so I very much hope that these kinds of materials are then accessible to people who can't be there in person. The class can only fit like 20 people anyway, so it's not one of these big lecture hall styles. But hopefully, putting the materials online help just a bit. Yep. Okay, let me do a demo. I'm going to do a quick demo to end this. So let me go back to the screen. So I've had some demos being requested. So here's what I'm going to do. I'm going to open something called Ableton Live, and this is an application that lets you make music, of course. So this is used by musicians all over the world. And I just have a demo version. I haven't even bought it. So first of all, I just want to check, can you guys hear this? Can you hear that? Okay, great. Okay, so check this out. Let's put in some congos. And break booty. This is some drum track. Okay, I'm going to put in another audio track. Let's turn down the volume just a little bit. And let's find something like hi-hat Dirty Doug. Yeah, whatever that means. One more. Let's get a techno beat. Okay, cool. So we got some music here. I'm going to go and grab an audio effect, a resonator. Okay, and I'm going to put that on the master track. So let's throw the Los Angeles resonator. Okay, so we got some music here, right? It's not Beethoven, but some good electronic music. And what I'm going to do is I'm going to open up an application that I built that you can find online under ML4A called Ableton OSC. And Ableton OSC is going to allow me to control Ableton from an application like outside of Ableton. So I'm going to select the tempo, and now I can control the tempo from here, right? You see as I move the slider. Okay, I'm going to grab the tempo, and now I'm also going to grab the master track, and I'm going to select the dry wet. That's the controlling the resonator, the dry wet trade-off between the resonator. And now what I'm going to do is I'm going to open yet another application called Covenant Predictor. That's right there. And hopefully it works. Yeah. Now I'm going to add 2 sliders to Covenant Predictor. And so now I can control it from Covenant Predictor. And what I'm going to be able to do is I'm going to train a neural network to control these sliders. So first I'm going to put like my phone in front of the screen, and I'm going to hit record, and I'm going to record a whole bunch of examples of the phone, and I'm associating this phone like as an input image to this set of slider values, right? So I get like maybe let's say like 50 or so samples. You move the phone around a little bit so you get nice diversity of samples. Stop. Now I'm going to grab, just like have myself in the screen, and let's make it go really fast. And let's turn up the dry wet. And now I'm going to record myself. So let's get like maybe 100, get up to 100 samples. I move around because I want to, generalize the network. I want it to be able to see me in different positions, right? So we're training a neural network right now. We're just adding recording data and associating these different images with the slider values in their current position. And then I hit stop. And now I'm going to change this to, let's go to the lowest tempo. Yeah. Okay. And now I'm going to actually, like, let's put myself out of the screen. Okay, so record a whole bunch of samples here with just me out of the screen. So it's just learning like my room here. Okay, let's get up to like 130 or so. And then I'm going to stop it. And now I'm going to hit train, and it's going to train the model for just a little bit. And now it's done training. And now I hit predict, and I'm going to control Ableton with the screen. All right, so it's pretty fun, right? And I can imagine musicians using this kind of stuff in the future. So yeah, that was a nice fun demo. And yeah, and again, all of this is available online. So if you're interested in using this, I'm using a demo version of Ableton, so there's nothing to pay for. So yeah, if anyone's interested in that, this needs to be an app. So let's go ahead and let's call it a day. So thank you everybody for joining me. This talk is going to be online on YouTube, I've been told. So I hope please do share it if you found it interesting and you think other people find it interesting. And please do go to ML4A and check out the Slack and yeah, let me know what you think. Okay, thank you everybody, and have a good rest of the conference. Okay, bye bye. Thank you.